Hello guys! Hello Philippines! I am a singer, eternal voice. Let's do the stoichiometry problem solving or the chemical calculations. Okay, yesterday chemistry, okay, chemical calculation, but it was not having a sound. I don't know why, so you have to repeat it. But yesterday there's no problems presented. Okay, now I need you to listen to me now because we will be computing at this moment the, the gram to mole ratio or vice versa. So again, we need to know that stoichiometry is the calculation of the amounts of the reactants and the products, the relationship of the reactants and products calculations. So we need to recall back to the basic principles and theories behind stoichiometry that the amounts, total amounts of the reactants will be equal to the total amounts of the products. Or in short, it could be stated in this way. The total number of atoms in the reactants should always equal to the total number of atoms in the product. Or the total number of mass of the reactants is equals to the total mass of the product. So, like that. It should be in steady state um, chemical reaction or in a chemical equilibrium. Again, the rate of the reaction of the reactant will always be equal to the rate of reaction of the product. So, in order to avoid confusion, we need to employ the linear algebraic expression such as letting x the number of moles of a certain compound and certain element to get the specific amount of number atoms, something like that. Because we need to know the total number of atoms. Of course, individually, we need to get the number of atoms. And then after that, getting individually, we need to sum our products. So in the stoichiometry, we have mole to mole ratio problem, gram to mole, mole to gram, like that. So using the relationship of the atomic mass unit, okay, the molar mass, okay, the molar mass, you know that one, okay, and then we need to employ the molecular weight if it is a compound, okay, molecular weight for the molar mass, right? Okay, don't confuse with that. I think it's just similar in comprehension, similar, meaning or the atomic weight. Okay, something like that. Okay. Now, yesterday, sorry. Yesterday, I introduced ammonia gas plus oxygen gas. The product will be NO2 plus H2O, like that. Okay. But there is also incomplete combustions. I don't know, I cannot identify yet. But I think the complete combustion is CO2, right? CO2 plus H2O. But the incomplete combustion will be uh, carbon monoxide, right? Okay. Actually, combustion refers to the hydrocarbon combustion. Okay, hydrocarbons. Okay. Contains of carbon and hydrogen plus oxygen, that's combustion. So in a gas, for example, ammonia plus oxygen, it is no longer combustion. Okay, gaseous compound, like that. So the same principle, the products, right? Analogy only. So rapid oxidation. So the product will be NO2 plus H2O. The same as, for example, methane plus oxygen, it will yield CO2 plus H2O. Okay, CO2 and NO2 have the same, characteristics, having one atom of nitrogen and one atom also of carbons, and two atoms of oxygen and two atoms of oxygen also in the CO2. Like analogy only, okay? So it's the same. like that. So I need to present to you, um, oh my God, really present to you a problem solving. Okay, so how can I do? Uh, I don't have the. This is my problem. This is my struggle. I struggle with this. Okay, we'll take the example by having the problem, right? Of course. I don't have the scratch paper anymore because I have so many scratch paper. Okay, so my God, what's happening? Okay, wait for a while. I have to write the problem first before anything else. Okay, sorry. Okay, glucose reacts with oxygen to give carbon dioxide and water. What mass of oxygen in grams is required for complete reaction of 25 grams of glucose? What are the carbon dioxide and water found? So this is completely word problem. The laptop first. Okay, okay. Because I play the video for my YouTube channel. So, because the time will be wasted like a use. Okay. Wait. That's the problem. Okay, I have to ready to be covered. Okay. Problem number one. Glucose reacts with oxygen give carbon dioxide and water. Okay. Mass of oxygen in grams for complete oh my god, it's happening. Reaction of 5 grams. What masses? What mass of carbon dioxide and water in grams are formed? Okay. So this is the problem. Okay. Glucose reacts with oxygen to give carbon dioxide and water. What fraction of 25 grams of glucose? What masses of carbon dioxide and water in grams are formed? Okay, this one. This is the problem for the stoichiometry problem. And we need to solve that. Wait for a while. Okay, the first thing, because in the problem, okay, this is a word problem. It was not stated the reaction. So in this problem, you have so many problems to be encountered. First, the chemical reaction, the reactant is equals to the product. Okay, you see this word problem, and then the chemical also are not written in a chemical formula. For example, glucose, right? Glucose reacts with the oxygen. So it is expected you should have knowledge what is the chemical formula of glucose in the first place, right? So that you cannot consume your time in opening the books or textbooks. For example, in an examination, if you don't memorize, if you don't remember what is the chemical formula of glucose, right? Because it's basic. It is a blood sugar. Okay, like that. So this is common in chemistry. Some glucose is very common. It's one type of sugar that is found in blood, something like that. Okay, so I will give you the formula for that. Okay, that is carbon 6H12 O6. So C6H12, say there is carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. So I will write now here. Okay. Reaction are represented as RX10. Okay. So glucose, carbon 6, H12, O6. Is glucose. Okay, this is the chemical formula of glucose of O6. Okay, like that. Then memorize this one, huh? Okay, this is common. Okay, like that. Chemicals. Chemicals. And water. Okay. In stoichiometry, we're not concerned of the phases if whether the carbon dioxide is a gas or it will appear as a liquid or a gas. We are not concerned for the for the status of the phases of the gases or any compound or elements. Okay, like that. Okay, we need to balance now the equation. So we should remember the total number of atoms of the reactant will always equal to the total number of atoms in the product. Okay. It's equal to the total number of reactant. Total number of atoms in the product, or stated in another way, total mass of reactant is equals to the total number of mass okay, like this, by theory and principle. Okay, the total number of atoms in the reactant equal to the total number of atoms in the product, or stated in another way, total number of mass of the reactant will be equal to the total number of mass in the product. Okay, this will be useful in the computation. For example, if you are required to ask how many grams of oxygen gas or carbon dioxide, then through this equation we can get the other masses of the what are presented in the equation. Okay, balance now. So I have to put this in weight, right? Here in the wall, this is the wall. Okay. Oh my gosh. Oh, nothing. I cannot put that in here. Okay. Then, let's go back. Let me carry this one here. Here. Sorry, I have to transfer. Like that. Okay. Hello. Okay. So let's balance the equation. We need to balance the chemical equation basing on the number of atoms, not on the number of mass. Okay. In the law of conservation of mass, okay, it should be the mass, the total mass of the reactant is equal to the total mass of the product. Law of conservation of mass. Okay. Like this. So glucose, let's balance the chemical equation, right? So chemical equation balancing. So glucose, carbon 6H12 O6 plus, okay, dioxide plus water. This is the chemical reaction or the chemical equation. Glucose, carbon 6H12O6 plus oxygen gas is equals to CO2 plus the water molecule. Okay, then balance it one by one. So let's start first with the carbon. Carbon in the reactant is 6 and carbon. So there is 6 carbon in the reactant, 6 atoms of carbon in the reactant, but there is no, then in the product, only 1 atom of carbon. So we need to put 6. So now, balance. Carbon C to the, let's take first hydrogen, okay, first to balance, okay, because it's just the same, it will be soft. Okay, let's start, let's do the hydrogen. Okay, hydrogen. Hydrogen in the reactant is 12 and hydrogen in the product is only 2. See here, 2. So we need, since this is 12 and this is 2, so 2 times 6, we need to put 6, right? So that it will become 12 to balance. Okay, so times 6 equals 12. Okay, so our carbon and hydrogens are balanced already. So the last one will be the oxygen. Oxygen in the reactant is equal to 6 plus 2 is equals to 8. Oxygen reactant is equals to 6 plus 2. Remember that always like this, huh? The number of atoms is equal to the coefficient times the subscript. The coefficient will be the numerical figure at the side of the element or the compound times the subscript, which is the bottom part of the compound. For example, glucose, carbon, 6H12O6. So this 6, this 12, and 6 are subscripts. So that we can understand better. Okay, like that. Okay. And then, not usually, but will become a number of atoms. Like that. Okay. So, our oxygen in the product is equals to 6. Sorry, it's happening now. Okay. So, sorry for the interruption. Okay. So this is 6 times 2 plus 6. So this is 12 plus 6. This is equals to 18. 18. So it was not balanced. We have 18 oxygen atoms in the product, and there is only 8 atoms of oxygen in the reactant. So we need to add more in the reactant, about 10 atoms. But the best way to do that is to employ linear algebraic expression. Okay, and we go back now to the reactant. We need to solve the algebraic expression in the side in which it is deficient. It is lacking because this is only 8 and here 18. So we go here to solve for algebraic expression. Okay, so we need to say let X is the number of moles of oxygen. Like this. Let X, okay, let X the number of oxygen, so it is equal to the coefficient. Since we have here, okay, so we need to state it individually. Okay, so 6, okay, plus X times 6 plus times 2. So times 2 it is coefficient times 2, and this is X times 2 plus 6 here. Number of X in this standalone oxygen, because here it is more complicated. There are carbon and hydrogen partners, so it will just complicate if we let the X in the compound. You should usually letting X in the solo element or standalone element, because it's okay. Why I'm not specifying here X6, right? X times 6. No, it's not there. It's always here because this is a solo. Okay, oxygen gas. And oxygen gas is the one we will find the number of atoms of oxygen. So this here is a glucose, a compound. We cannot separate, okay, during the algebraic expression. Okay, so we here oxygen alone. Okay, here is glucose. So we are not considering this oxygen in the glucose. We are referring to the oxygen element. So 6 oxygen in the glucose, which is 1 times 6 equals 6 plus X times 2 is letting the X the number of moles of oxygen times 2 coefficient times subscript, okay, equal to the right, which is 18 oxygen, right? Like this. Okay. equals to 18. Okay, this one. So 6 plus x times 2 is equals to 18. Do the math. Loss of oxygen in the reactant will be, okay, 2x is equals to 18 minus 6. So x to 12. 18 minus 6. 18 minus 6 is 12. So x is equals to 5. No. No. Okay. Algebraic expression. 6 plus 2x is equals to 18. Solve for the value of x. Our x will be equal to 12 moles of oxygen now. Okay, we need to put that here now beside the here. Okay, like that. So it will now become like this. So glucose plus 6 moles of oxygen gas is equals to 6 moles of carbon dioxide plus 6 moles of water. Okay, so the oxygen now is balanced. And we have to final balance the equation starting with carbon. Carbon 6, carbon 6, okay, hydrogen 12, hydrogen 12, and oxygen 12, okay, plus 6, 18, okay, 12 plus 6, 18. Already 18 here, so 18 plus 18, 18 is equals to 18 in the reactant product. So these are now balanced. We can now solve the problem, okay, in this chemical reaction. Glucose reacts with oxygen, again, okay, this one is our problem. Glucose reacts with oxygen to give carbon dioxide and water. What mass of oxygen in grams is required for complete reaction of 25 grams of glucose? What masses of carbon dioxide and water in grams are found? So what are being required are the mass of carbon dioxide, mass of water, and the mass of oxygen. Okay. So 3, we need to solve 3 masses. Okay. Our given, the given is 25 grams of glucose. Other given, okay, plus the chemical reaction involves number of atoms and number of moles, in which it is very helpful to solve what are being required. Okay, so our given is 25 grams of glucose, which is carbon 6, H12O6. Okay, and required 3 masses, right? Mass of oxygen, mass of carbon dioxide, and the mass of water, like this. These are required. The grams of oxygen gas, the grams of CO2, and the grams of water. All are masses. 3 masses are being, okay. And now we refer to the balanced chemical equation. Because we can solve that by using this balanced chemical equation. Okay, like that. Now we will start to mass of oxygen, grams of oxygen. Okay, first number 1, something like that. Okay, 25 grams of glucose. So we will start our solution grams of glucose. 25 grams of glucose, C6H12. So We will start from 25 grams. Through that, we can get the grams or the mass of oxygen gas in relation to the balanced chemical equation that we solve like this, getting the grams and moles. We need to employ the basic theory and basic principles, okay? Mole, molar mass, molecular weight, atomic mass. Okay, now since this is glucose given, we need to compute for the molar mass or the molecular weight. So in our basic chemistry, if we compute for the molecular weight or the molar mass, we need compound. Okay, and then we will multiply the number of moles to the atomic mass unit of that element, AMU. Okay, for example, this one, glucose, carbon 6. Okay, for the carbon, 6 times 12, because the atomic mass unit of carbon is 12. Okay, plus 12 times 1.008 grams for atomic mass unit of hydrogen. Okay, plus 6 times 16, because oxygen has 16 atomic mass unit in the periodic table. Okay, I did not refer the periodic table because I already memorized the most common elements atomic mass units. Okay, because it will consume also time to refer to the periodic table, where in fact these are common elements. Will cost you a long time to just getting the atomic mass unit of oxygen, which is in the first place, can be memorized. Okay, like that. It will take time because elements, so many elements. Okay, then that's why you should also choose the most common elements and memorized the atomic mass unit. Anyhow, if you will memorize that one for the first time, second time, it will retain in your brain. It will accumulate to your brain, I think, for how many years, something like that. For example, me, I graduated in like 1999, something like that. But then now 2020, how many years? It is 20 plus years, something like that. And then it still remain that I know that the oxygen has an atomic mass unit of 16, hydrogen has 1.008 ANU, and carbon has 12, like that. So if I will not memorize that one, I will refer it back to that it will take time for me. Okay, that's why it's better to memorize that as early as possible, something like that one, because chemistry is a subject for all courses. There's no exemption for this. All courses, Bachelor of Science courses, have chemistry. It's not only engineering, though the chemistry of the BS Chem and the chemical engineering, I know that, but still you have to do that with problem solving also in chemistry, and all of us will learn chemistry, and we have to memorize the elements, their atomic mass units, and their formula like this. Okay, so like that. So I will write now the molar mass or the molecular weight of glucose. Okay, for the purpose of discussion. Okay, so I need to get the molecular weight. I have to abbreviate. So like this, molecular weight or molar mass. It's just the same. Don't be confused. Molecular weight is equal to carbon 6 times 12, hydrogen 12 times 1.008, okay, oxygen 6 times 16, okay, that is 76, 6 times 16. I'm not good at math. Okay. Okay. So it's this one. Carbon, okay, 6 times 12, hydrogen 2 times 1.008, and oxygen is 6 times 16. individually sum up. That would be your molecular weight or molar mass of that particular compound. Okay, 72, 12 times. I will use calculator especially for atomic mass unit as a decimal point. Okay, 12 times 1.008, so 12.096. I will just use calculator for the purpose. It will speed up the discussion. Okay, plus 96. Molar mass or molecular weight will be equal to 72 plus 12.796 plus 96. So we have 180.096. Okay. This is grams per mole. Okay, grams per mole. So the total molecular weight of the compound glucose is equal to 180.096 grams per mole. This is the molecular weight or molar mass. Molar mass is derived from the unit, which is grams in the numerator and moles in the denominator. That is why it is called molar mass. But it's just the same with molecular weight of a compound. Now, this is very useful in the conversion factor. Okay, if you have 1 mole as a reference, we always considered 1 mole of a certain element or a certain compound. So 1 mole of glucose will equal to 180.09, which is the molecular weight grams. Okay, like that. But it could be this one only. Okay, this will be our conversion factors. 180.096 is one. It depends on the what could be not reversed like that. Sometimes it will be mole over gram, gram over mole. It depends on the situation. Okay, when we solve now. But I am telling you only that 1 mole of glucose will be equal to 180.096 grams molar mass. So we will always use that conversion factor during our calculation to solve for the grams of oxygen, water, and carbon dioxide. Okay, something like that. Now we will now solve. Okay, grams of oxygen now. We solve for grams of oxygen. Okay, we start with what is given. Of course, we'll start what is given. Okay, given is 25 grams. First, we'll start what is given. Okay, given is 25 grams of glucose to produce that is. So 25 grams of glucose. So in not cancelled out so that it will reduce or simplify what is being required. So if we are directed to cancel out one of the variable or one of the units, then we need to adjust it. Okay, upon multiplication or division like this. Okay, we have 25 grams of glucose. So we have the conversion factor of 180.096 grams per mole. Okay, and then the grams is in the coefficient of glucose. We cannot cancel that one directly. If we will multiply that one, okay, take note. Our purpose is to simplify what is being required. Then how can we simplify and obtain what is being molecular weight or molar mass to these grams of glucose? It will not cancels out. Then you have to reverse this one per 180.06. Okay, that 1 over 180.06, multiply that here so that the grams will be cancelled out. What is being left is the number of mole. It's very clear. Okay, because we cannot cancel it out if we multiply directly to the molar mass and the molecular weight. So we have to reverse. It will be 1 over 180.06. Okay? If you reverse that one, you should also reverse the unit. The grams will be at the bottom and the mole will be at the top. Okay? Because you reverse that one for the purpose of cancelling out what is being common to simplify what is it's useful for what is being required. Okay, 1 over 80. 1 over 180.096 So this is, see, this is reversed. Okay, so we can cancel out the grams. We can simplify. Okay, the more units staying, the more it will become complicated. So as much as possible, you have to reduce the units in a particular calculation so that you can easily target what is being required, right? So it will confuse you. You have so many units that will not be cancelled out. So that's why you have to reverse this molecularly. So what is being left is the number of moles. Okay? It will cancel out the grams. Okay? Like this. And then multiply again. Now this time, since there's no other option, we will use the chemical equation, the balanced chemical equation here. This one. Okay? This one. Sorry. This one. So, 25 grams of glucose to produce grams of oxygen. So you need to be alerted by that. To be quick, you call it one, observant, because we need to have the mass of oxygen. Of course, you need to consider the relationship between oxygen and glucose in this chemical equation that is balanced already. So what is being left is the number of moles. Of course, you have to take the being remained. You simplify that one, cancels out the grams, and what is being remained is the number of moles. Of course, you need to simplify that one. Okay, then you have to multiply that also in terms of moles relationship. Moles of glucose, we can compute for the grams of oxygen, right? Like that. We will start to the moles of glucose in the denominator. Okay? So that we can cancel out also. Okay? This is small for the glucose, right? I don't have to put the formula. I will just put, sorry, I'll just put glucose. Okay? Glucose. So, in the balanced chemical equation, as you can see, the balanced chemical equation, how many number of moles does the glucose have? Observed properly. Okay, glucose, carbon 6H12O6, the reactant. So it is 1 mole, right? 1 mole of glucose. Okay, so we need to put that in the denominator for the glucose. Okay, 1 mole of glucose. Okay, 1 mole of glucose. Char, like this. So our relationship with the oxygen, it will produce later on after the completion of the reaction. So we have 6 moles of oxygen. Okay, 6 moles of oxygen. Right? So we need to put 6 moles of oxygen at the numerator. Okay, 6 moles of oxygen, in which it will cancel the moles of glucose. So the moles of glucose now has been cancelled. What is remained is the moles of oxygen. So through that oxygen, okay, we can now determine the mass, right? Again, using the conversion factor, which is 2 times 16. This is 2 16. Okay, 2 times 16. So we have to put the atoms of the here, somewhere here, oxygen gas. That is 2 times 16, 32 grams per mole. This one is in the side, 32. Or atomic weight. It's just the same, don't be confused. Okay, so this is the conversion factor. And now, we will multiply that here. Okay, be sure that upon the multiplication, it will cancel out the number of moles of oxygen. Okay, since the mole is in the numerator, so the mole must be in the denominator. So you will multiply it directly with 32 grams per mole. Okay, so times 32 grams per mole of oxygen, so cancels it out. So what remains is grams. So what remains is grams. grams of oxygen. We can also solve the oxygen, grams of oxygen here, which is being required. Okay, so our grams of oxygen will be equal to, okay, 25 times 6, 25 times 6 times 32 equals divided by 180.06. So our grams of oxygen is 26.65 grams. 26 grams oxygen. Okay. So our first is 26.65 grams of oxygen. Okay, same thing. Okay, the same thing. You will be able to do this for this. Okay, okay, like that. So we need to get another scratch paper. Okay. Oh my gosh. Sorry. That. And I will tell you different at the end. Okay. This is only my own style. I will tell you later. For the purpose of easy to understand, something like this. Okay? So for number 2, grams O2, we have first the 25 grams of glucose. Okay. I will go directly without showing you. Okay, because you understand already the first solution, which is in the same manner only. So 25 grams of carbon 6H12O6. Okay, multiplied by 180.09 glucose. Okay, see? 25 grams of glucose, taking the molar mass and molecular weight and cancels out the number of moles and consider in the chemical equation, balance equation. Okay, this one is that again. Always refer to the balance equation. If the remaining being required is the moles left reaction at the top. Okay, so 1 mole, still 1 molar of glucose. Okay, sorry. Okay, 1 mole of glucose, C6. Okay, 6 moles of carbon dioxide. Okay. And taking the molecular weight and molar mass of carbon dioxide, which is 44 grams. And taking the molecular weight and molar mass of carbon dioxide, which is 44 grams per mole. Carbon 12, oxygen 12 equals to 44. Something like that. So, okay. By the way, you don't have to stay individually. You have to memorize the carbon that has molecular weight of 44. Okay, then it will be retained in your brain. You need to complete one by one also. But if you want, it depends on you. So 44 multiplied by 44 grams per mole, because it cancels out if you put this way. So what will remain is the grams of CO2. This one. See? Multiplying it directly, you don't have to reverse, because if you multiply that, the 44 grams per mole, it will cancel out, and what remains will be the grams. And we, okay, like this. In the same manner, okay? But for the third, I will show you something. Charot. Okay, 6 times 44 is equals to 67 grams of carbon dioxide. This is the second answer. The first, 26.65 grams of oxygen. The second, we need to compute the grams of H2O required for the complete reaction. If we have initially a 25 grams formed after the reaction, with a chemical reaction, something like that. Okay, actually, we need to solve in this manner, actually. But still the same like this, okay? Take this, so it will take time. We need to use the mass of the reactant is equal to the mass of the product, something like that, okay? Sorry, total mass of the reactant is equal to total mass of the reactant. Okay, done. The products, right? Okay, our reactant is here, glucose plus oxygen gas. Yes, this one. This one. Oh my gosh. This one. This is the final balance chemical equation, right? So we need to get the total mass of reactant and total mass of the product. So mass of glucose plus mass of oxygen gas is equal to the mass of carbon dioxide plus mass of water. So through that equation, we can solve for the mass of water directly through that linear algebraic expression without considering this too lengthy equation that we presented a while ago. Okay, like that. So grams of sucrose, which is given 25 grams. Okay, so let's put the equation back. O6 plus 6 oxygen gas is equals to 6 CO2 plus. Okay, so this one, oh, right, this one. The total mass of the reactant is equals to total mass of the product. The total mass of the reactant comprises of the glucose plus the oxygen gas. And the masses of the product comprises of carbon dioxide and the water molecule. Then add that individually. Okay? So we have the mass of glucose, which is given in the problem 25 grams. Okay? And we have the grams of oxygen that we already computed a while ago, that is 26.65. And we have the grams of CO2 that we also computed as 36.67 grams. So what is left is the grams of H2O, right? This one. As, okay, 26.65 grams of oxygen gas is equals to 36.7 grams of carbon dioxide plus unknown grams of water. So actually there are two methods how to compute the grams of water, by using the mole-to-mole ratio and by using this law of conservation of mass, in which total mass of the reactant is equal to the total mass of the product. So we cannot solve the grams of water. I prefer this one compared to the other one because it's lengthy. Okay, and if you get wrong with the molecular weight, for example, then your answer will be automatically wrong, right? So whereas this one, it will be balanced somewhere along the way if you compute for the grams of water, because this is algebraic expression, right? Linear algebraic expression is very easy to solve for the value of molecule, okay, like that. Okay, let X as the grams of water, but actually it's automatically the water for the purpose of algebraic expression only. Because in algebra, always using let y the value of something, let x the value of something, so that you can solve for that required through that given problem, something like that. Okay, so the grams of water will be simply equal to, okay, add this one. No need to one by one because it's very easy already. This is linear, okay? Okay, only linear, no x, y, z, x, y, something like that, raised to the power 2. No exponential, you know? So it's very easy to manipulate, something like that. Okay? So 25 plus 26.65 minus 36.67. So the grams of water will be 14.98. Okay. 14.98. So in this linear equation, the mass of water is equal to 14.9, which is that in the product. If the product total mass is equal to the total mass of the reactant, then bingo, it's perfect. It's already balanced. That's why it's called chemical balance equation, right? So meaning the total number of masses in the reactant is equal to the masses of the product. So if it is still imbalanced, there's something wrong in your computation. So that is no longer obeying. This equation is employing the theory of law of conservation of mass. Okay? Or we can state that in another way around in terms of atoms, total number of atoms during the balancing of the equation. So the total number of atoms will be equal to the total number of atoms in a reactant is equal to the total number of atoms in a product. Let's say if it is really equal, okay? Okay, again, this one, this one. So let's go back, okay? Here. Reactant, carbon 6, am I correct? Hydrogen 12, and oxygen is, oxygen, okay. 8 plus 12, okay, 6, okay, 6 plus 12, okay, plus 18. Oxygen, hydrogen, and carbon. Okay, and the other side, carbon, hydrogen, and oxygen. So carbon 6. Okay, 6 plus 12. Okay, is 18. This one. The total number of atoms must be equal. This one. Okay, CHO. This one. From the reactant is equal. It's 36. Okay? Tama ba? 6 plus 12 plus 18 is 36. There are 36 total number of atoms in the product, and there is also 36 total number of atoms in the product. So it is equal. So it is in the steady state equilibrium. Okay? Because the total product, or stated it differently, the total number of masses in the reactant is equal to the total number of mass in the product. So all of them obeying the principle of the law of conservation of mass. Okay? Okay, like that, in stoichiometric chemical calculations. Other problems will always be like this. Okay, and there's something of confusions will be involved. For example, carbon dioxide is going to the pipeline, something like that, and there will be a volumetric flow rate, something like that, in let's say liter per hours, cubic meter per second. So that is volumetric flow rate, the flow of gases in the pipeline. So you have to involve also this type of equation that you can connect of what I am discussing in the ideal gas law. You have to connect those equations there and here, something like that. But the problem mostly arrive because the problems doesn't state the reactions in the problem sometimes. We will just say glucose react to something in words. So if the students cannot understand what is the formula of this sucrose, glucose, so if you have to research, but if it is an exam already, it's very difficult to research in the books. It will take time. There are a lot of problems. For example, 70 problems. Okay, like that. And in the number one problem, we do not know what is the formula of sugar, something like that. Sugar react with oxygen. Sugar. Okay, that's the problem. The formula of sugar is carbon 12 H22O11. So if you don't know, trouble. If it is okay, if it is the common name, for example, muriatic acid react with blah blah blah, and muriatic acid is equal. There's a lot like that. The trade name, the trade name only they will use it, or the general name, something like that. Or the table salt will react to water to produce blah blah blah. How many grams of blah 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 in order to be formed with this blah blah blah, something like that, and you don't know what is the formula of table salt. So it is sodium chloride, something like that. Another example, sodium bicarbonate for the baking soda plus water, something like that. You do the formula of the sodium bicarbonate baking soda. So chemical formula of baking soda is the sodium bicarbonate, something like that. So it's very difficult, really. Okay, so that's why you have to memorize the most common chemical names or chemical trait names, because sometimes we will not really put in the chemical formula on the problems. Okay, good. If that is the case, that there's already reaction. All you have to do is to balance the chemical equation. Then perfect. It's there, but if it is not there, you have to be clever enough to memorize the common chemical names, something like that. Okay. So this is an example of stoichiometric chemical calculations. I hope you enjoy because I'm explaining this to you very slow. Okay, very slow, meaning spoon feed. Okay, spoon feed in a detailed fashion of teaching methodology. Okay, so it's just like an elementary discussion. Okay, step by step or stepwise discussion. Okay, any questions so far for this stoichiometry problem regarding glucose reaction? Okay, like that. This is common, usually common, the combustion, oxygen, rapid oxidation always, most of the time. Okay, the monoatomic gases usually, especially in gases problems. Okay, because real gases will not behave ideally, of course. So sometimes it will not be, in the problems. Most of the time, it's always like this: carbon dioxide, oxygen, in O2, blah blah blah, like this. The most common. Okay, like that. So I hope you enjoy this discussion. Then if you have confusion, you can refer to your textbooks, chemistry textbooks, or sometimes you can also Google that one in the internet. Okay, so, because if you try to Google the internet, okay, you're not allowed to use data during the examination. So how can you obtain the formula of that? You cannot Google it in the actual examination. So all you have to do is to memorize that one. Okay? If it's all in physical properties, right? As you remember. So there's a lot. For example, the viscosity point, the melting point, the freezing point, point, the flash point, something like that. There's a lot in the table of the physical and chemical principles, characteristics of those elements. So many, and you have to trace that up there. Okay, if it is open book, okay, chemical formulas, so that you can solve directly what is being asked to the particular question. Okay, thank you so much for listening to this discussion. Okay, if you think you like this video, just comment, like, subscribe, and then you have to click the notification bell for some new updates of I Am a Singer Eternal Voice channel. See you later for other topics of chemistry. This is I Am a Singer Eternal Voice. Sotero. Thank you so much. God bless everybody. Bye bye.